Okay. Well, good morning, everyone. My name is Vladimir Gurevich, and we actually assembled a big team of P4 enthusiasts and contributors to talk to you about the language. So I'll start first and talk to you about the very basic concepts of the language. And okay, everything is working. Why we really needed to have P4, I think Nick talked about that, but I'll just briefly remind you that in the real networking systems, we have a hierarchy of so-called planes, or basically the algorithms which work on these systems. So at the very top sit very nice interfaces, sometimes GUIs, sometimes very fancy systems which allow us to control multiple boxes, and that's called management plane. And then, of course, there are famous routing protocols and everything that makes the box really work, and that's called control plane. And initially, when people were designing those boxes, at some point in time, they would code some very, very specific pieces in highly optimized assembly language to do what they would call a fast path switching. So that would be the routine processing of the packets very quickly. And so that's what we nowadays call the data plane algorithms. Little by little, people figured out that actually they can get some specialized hardware that would do the switching for them. But with that specialized hardware, what came is the fact that the actual algorithms and how you would control those algorithms would be determined by the vendor of that hardware and not by you. So if before, the designers of the network operating system would go down to the person who was really good at assembly language programming and tell him, well, I need this and this to switch my packets fast. Nowadays, they couldn't do that. And so P4 is really there to address the problem. So now you are allowed to write your own data plane software. So when we designed the language, there were 3 goals that we tried to achieve. So first, it should be protocol independent. That means that you are allowed to code your own protocols, so define the packet headers and subsequently define the parser, which allows you to parse exactly the packets that you are interested in. And also, you should be able to define your own set of match and action tables. That they form the core of packet processing in P4, and subsequent presenters will talk about them in details. The other goal that we had in mind when the language was designed was really to make it a high-level target-independent language. So when you write a P4 program, unlike the older days of assembly language programming, you do not have to worry about the details, how the packets are actually processed on the system, the microarchitecture of the chip, and so on. Nevertheless, the P4 allows you to program the systems very, very efficiently because you are able to express exactly what you want to do with the packet. And in order to be able to do that, P4 requires a compilation step, and P4 compilers are actually quite sophisticated because they are able to translate those fairly high-level constructs in a very, very target-specific configuration that is usually required by the modern switches that operate at very, very high speeds. And the third target, the third goal for P4 development was our desire to be able to reconfigure the hardware in the field. So same way how you can load a new app or a new program on your phone or on a new computer, same thing should be applicable to the networking devices. You should be able to load a new program whenever you need to support a new protocol, and the system, the networking system, should be able to suddenly get the new knowledge of a new protocol, or maybe forget about the old protocol which you don't need and dedicate those resources to something else. So how does this all work? Well, basically, it all starts with the device which has not yet been programmed, and therefore is just a generic packet processor which doesn't know about any packet formats, about any protocols, about the fact that there is IPv4, that there's a TTL that needs to be decremented, or anything like that. And what you need to do, as when you take a processor which doesn't know about what it needs to do to perform any particular calculation, you need to author a program. And so you write a program. Those programs have extensions, .p4, of course. And so in this case, it might be a fairly simple program first, which just allows you to do basic L2 and L3. And then, as with any other computer program, you need to compile it. And compiler produces two results. So one result is actually special configuration that can be loaded onto that switch. Same way like we'll start running a program on any computer. And so that is when the switch actually gets understanding of particular networking protocols. Suddenly it becomes aware of what an Ethernet header is, and after the Ethernet header, there could be a VLAN header, so that's how we program the parser. And then after that, there could be IPv4, IPv6 header, and so on. And subsequently, it also programs the match and action tables so that you can perform exactly the algorithms that you need to switch these particular packets. And the other result of the compilation of a P4 program is an automatically generated API. So as you will see at the end of this presentation and throughout while we will be discussing about P4 programs, they're very, very amenable to automatic generation of APIs because effectively, besides just defining the data plane, so the processing algorithm for the packets that follow sort of horizontally on this picture, P4 program allows us to deduce how the control plane will look like, and so which particular APIs are required to control the objects defined in your P4 program. And so once this runtime API is generated, then you can basically make sure that your network OS uses this runtime APIs. Usually there might be some low-level drivers that are required to communicate with a particular device that runs P4 program, but ultimately you will be able to start programming those tables, put the routing entries, forwarding entries, what have you, and the whole thing will work. Now, later on, you might decide that you need another protocol added. So you might change your program, rename it called vxlan.p4, repeat the same cycle, so you will compile and load it on the device, and suddenly it will start understanding what UDP header is and what's the VXLAN header behind that, and so on and so forth. Obviously, there will be new tables that will be also configured on the device, and you will have to regenerate the runtime API because it will now have more functions and more tables to work with. But as long as your switch OS can be adapted to use this, you should be able to do this and reuse the same hardware for a long, long time without worrying about it getting obsolete with the invention of new protocols. So that's kind of the basic workflow. How do we achieve this in the language? There are very few concepts that you need to be aware of. So basically, P4 is designed to program what we call pipelines, and those pipelines have 4 components in them. So the first component is a parser. What you need to do when the packet comes in, it's just a series of bits or bytes, and the parser should be able to identify particular networking headers inside that sequence of bytes and convert it to what we call the parsed representation of the packet. So you don't have to worry at which offset where exactly a particular field is in the packet. The parser will find it for you, and after that, the P4 program will be able to refer to that field. The other component of P4 program that you're allowed to use are match plus action tables. And so match action tables, that basically the heart of your processing. So if you think about them, they're just basic functions which map certain fields or headers into the outcomes, which are actions and action data, and we'll talk about them in detail. So these tables can be sequenced, and as a result, you can get fairly complex actions expressed in the language. The reason we use this particular constructs instead of imperative statements most of the time is because they are most efficiently implemented on the existing hardware that we have everywhere in the world. The third component is called the deparser. It has to perform the function which is opposite to the parser. It has to take the parsed representation of the packet and serialize it back on the wire. And the last component, which is the most important, is the metadata bus. So whenever the packet passes between these components, parser, match action tables, and deparser, we need to pass the intermediate results. And so the way we do it is by carrying what we call a metadata. It's just a set of fields, same like a C structure, or you can think of it as a very, very wide register array. And that's how the results of computations are passed from one stage to another. So pretty much all these components, except the metadata bus, I would say, are kind of optional in the language. You don't, depending on what kind of device you work with, you might or might not have to program these. So here are some examples how we can use those basic pipelines to form a hardware that we're more familiar with. So here's the how a typical switch looks like. So in the typical switch, we usually have more than one port, and as a result, all the switches have to solve the same problem. So they have to figure out what to do when multiple ports send the traffic to a single port. Obviously, that can result in some queuing. And also, they have to figure out what to do when a packet sent from one port needs to be sent to multiple times on the same port, or to multiple ports when we do broadcasting or flooding. And so as a result, all the switches are structured the same way. They have two pipelines, ingress and egress pipeline, and in between sits a component that is responsible for packet queuing, replication, and usually scheduling as well. So as you see, there could be several different configurations, and really which configuration you need to use depends on the particular switch architecture. So sometimes you'll do parsing and deparsing on both ends of the pipeline. Sometimes, you know, the inner deparsing and parsing stages can be skipped. It really depends on the architecture of the device. Simple NIC card, that basically contains just two pipelines without anything. One pipeline is responsible for delivering data into the network card. The other one is to deliver it out of the network card. So there is nothing in between them. And then you can think about some protocol plugins which usually receive parsed representation of the packet and just need to perform some operations. That's usually useful in the software. So in that case, you don't have parser or deparser in the protocol plugin. You already operate on the parsed representation of the packet, and that's the output. So P4 allows you to basically define all these and many more types of devices. All depends on what you put in your program. So as a result, there are three sections that you will typically see. So the first section is responsible for data declarations. That's where you can define data types that represents your header and that represent the data that you carry over the metadata bus. The second section in the program, if you need to use parser or deparser, consists of a series of states and transitions between them and show how a packet can be parsed. And the third section of the program is called control flow program or control flow function that defines a series of tables and as well as some imperative statements which show how the packet needs to be processed and basically express your data plane algorithm. So the further instructors, what they will do, they will just go through the section, through the language section by section, and show in detail how all these things work. And now let me introduce Ben Pfaff, who will talk about Parser.
Thank you, Vladimir. I feel a little nervous up here because there are people in the room who've been involved with P4 a lot longer and know it better, and if we're lucky, they won't jump up and down and yell, no, 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 you're wrong in a subtle but important way. One thing to keep in mind here is that we're talking about P4, oh, he's already got a correction. Is that we're talking about P4 102. There are newer versions that are under development that have some exciting new features, but 102 is the one that's most deployed so far, so we're going to talk about that today. So I'm going to go mostly over those sections at the beginning of the program, the data declarations and the parser programming. And then after that, we'll have some other people up here to talk about how the packet goes through tables and actions and those control functions and so on. But one of the big points to remember is that P4 is not exactly a traditional programming language. It looks like it in some ways, but it doesn't have a lot of constructs like pointers and loops and so on. Because, well, for one thing, those aren't in the switch hardware typically, and second, you don't generally need them to switch packets around your network. These are actually fairly similar to the restrictions of eBPF that's going into Linux to implement some of these in software. So let's talk about header fields in the parser. So your P4 program typically starts with some declarations of headers. So you can see that there's a couple of header type declarations here. One's for a basic Ethernet header. You can see that each of the fields is declared along with the number of bits that it includes for the Ethernet header and for the VLAN tag. And then afterward, we have to take these types and instantiate them. So there's typically only one Ethernet header, so that has just a single declaration. But often VLAN tags can be stacked into multiple. And in that case, you have to say what's the maximum number you intend to support in your program. So here, it's declared a lot like a C array of 3 elements. That doesn't mean that you'll always use all of those. But they're available. So one of the things to keep in mind is that even when you instantiate it, that doesn't imply that header is present at any particular part of the packet that you're looking at. That comes later on. So in addition to declaring actual headers that you find in packets, you can declare header types that don't actually correspond to anything you'd find in a header. You can use these as sort of a temporary storage in your program. They look just like a header type declaration for packet contents, but there are some important differences. You do have to instantiate them just like you would regular headers, except that you write metadata instead of header. So here's some of the differences between actual headers and metadata. When you write the field declarations in a header, you care about the order, you care about the sizes because those have to correspond to what they are in the actual packet. For metadata, well, you need to give sizes, but the layout doesn't matter. In addition, real headers have to total up to a multiple of 8 bits. And presumably that's easier for hardware. It's definitely easier for software if all of your headers work out to even byte lengths. But probably the most interesting difference is that packet headers have a concept of validity. And validity just means, have you actually parsed this out of your packet? If you have room for 3 VLAN headers, but the packet that you just parsed only had 1, then only the first VLAN header is considered valid. Metadata, on the other hand, it's just temporary storage. So if you haven't assigned anything to it, it's just initialized to 0. And then finally, packet headers can have variable length fields. Let's talk a little bit more about variable length fields. So here's how you might declare an IPv4 header. It has a bunch of fields that are fixed length, and then it has a field there called options at the end, and that just has a length that says star. And that means this field is variable length, and it uses up the rest of the length of the header. So P4 figures out what the length of that is based on your declaration for the length of the overall header. And in this case, you can see that that declared length is the IP header length field, IHL, shifted left 2 bits, same as multiplying by 4, which is the standard way of computing the length of a IPv4 header. There's also a declaration here that the maximum length of the whole thing is 60 bytes, which presumably the compiler could also figure out on its own, since the maximum value of a 4-bit field is 15, and if you multiply that by 4, you get 60. So now we've got all these declarations for individual headers, and we need to define a program that explains where the headers actually go in the packet, and this is the parser program. That has a pretty simple format. There's a few types of imperative statements. The parser program starts out with the start parser there, and you can see that the first statement there says extract Ethernet, and that means that at the beginning of your packet you find the Ethernet header. The implementation at that point will copy all the information from the current point in the packet into that declared Ethernet header, and then advance the current pointer. So the second statement there, and this is typically the last statement in a parser, says what comes afterward. So that's phrased as a select in this case, and that's looking at the ether type field in this Ethernet header that we just parsed, and going on to the next header based on what that type is. So we can see that 8100 and 9100, those both indicate a following VLAN field. So parse VLAN tag in that case says to jump to the parse VLAN tag parser. We see that has an extract of its own, and that uses a special syntax that means extract into the next available VLAN tag in our stack of 2 of them. And then it has its own select statement for going on based on the ether type there. You can see that there's a slightly different form there where to parse the next VLAN tag, it's actually using a masked form instead of specifying them explicitly. So both of these parsers also have a word in there that says ingress. So that is not the name of a parser, that's the name of a control function. And that means that if we hit that state, then we're done parsing, and we can go on to the control program. So here's a few more declarations that we might find there for pulling in the IPv4 and IPv6 headers. We can also hit exceptions during our parser. So for example, suppose that we had a whole bunch of stacked VLAN headers, and since we only have a 2-element array declared, that would mean that we'd overrun our array. So in that case, P4 calls a standard parser exception that corresponds to an index out of range. And in this case, we have that parser exception defined to just go to ingress and starts the actual control program. So P4 also has a concept of calculated fields, which are used for checksums. So it can both verify these fields when a packet comes in and recalculate them when it goes out. So we can see an example of that here for IPv4. We start out with a field list, which lists all the fields in the IPv4 header that are included in the checksum. And then we have a declaration of how to calculate the checksum based on those fields, which also states the particular algorithm we're using and the width of the output. And then finally, we have a declaration of the calculated field itself, which says that on ingress, we should verify it using that IPv4 checksum we declared, and on egress, we should update it. Bob, do you have a?
Is the algorithm hardwired, or are you going to show how that calculation is specified?
So P4 has a list of algorithms. Each of those, I believe, is hardwired. At this point, in 102, I think you just get a choice of one of several algorithms. I can't recall whether P4 1.1 and 1.2 introduce programmable algorithms. It would certainly be a new feature.
Some of those words or the tags are actually color coded. What do they mean? Are they reserved?
So I believe that the ones that are blue are just to show you that that the IPv4 checksum is using the field list that was declared earlier, and the calculated field there, that's I believe that's referring to the IPv4 a field in the IPv4 header. So I don't think there's anything real magic there. It's just saying that that they're referring back to things we declared earlier.
So what about this P4P checksum? Are you going to define the behavior of that at another place, or is that reserved?
Okay, I believe that P4PE checksum is in fact a predefined parser exception that gets invoked when a checksum fails. So it's saying that that in the case of a checksum failure on ingress, we drop the packet. You could of course do something else. We've seen most of what I'm going to show about P4 parsing. Here's one thing that's slightly more advanced. Instead of doing a select on just a single field to decide which parser state we go to next, we can do a select on multiple fields. And in that case, the values of those are just concatenated together for the purpose of the select. So in IPv4, you might naturally want to go on to the next parser state by looking at the IPv4 protocol, and you can see that in the final 2 bytes of each of these. The ICMP is protocol 1, TCP is protocol 6, UDP is protocol 17 or hex 11. But in this case, it's choosing to also select based on the length of the packet and the fragment offset. So in this case, you can see that it's only selecting packets that have no frag offset and that have a standard length IPv4 packet with no options. So I don't know whether that's a typical use case, but it shows the sort of thing that you can do. So finally, at the end of the pipeline, after we've gone through all of the match action tables and so on, we have to reassemble the packet in the deparser. P4 102, I think it has maybe a couple of sentences about what the deparser does. It's a very simple description. And basically it says that you reassemble the packet the way you took it apart. This is simple and clever, but in later versions of P4, we've taken some steps toward making the deparser much more explicit so that you can reassemble packets in different ways.
Sorry. So if you want, before the packet is leaving the device, if you want to add more tag or something, change the existing tag, that is done by in VMware?
So the deparser would be responsible for taking whatever changes you made to the packet headers. For example, in the P4 control program, you could add an additional VLAN tag header if you had that stack around. and then reassembling that into a packet. Yes, this is where the tags would be added. I believe now I'm turning things over to Johann to talk about actions.
So thank you, Ben, for getting the packets into the system and actually making us understand the fields in the packet headers. The next step in the day in the life of a packet would normally be to find out what to do, in other words, to classify or to match, but then followed by the actions to actually do things to the packets. But because we know you are more awake in the morning and then decline towards lunchtime, we thought we'd do the more energetic one, the actions first. So here are the actions you can apply to different packets. The no-op packet is, of course, the simplest one. You don't do a lot there. But it's actually sometimes quite important as a placeholder for other actions to come. The drop action, very important for security, to go and discard a packet. With those two, you already have a simple firewall. Then there are a group of actions that actually change these fields that we got from parsing the packets. So there would be modify a field, different kinds of modifications. Then there are different add operations. The one just called add takes two values and computes the sum and stores it somewhere else. Add to field you can look at as an increment by a certain value. So it actually is a plus equal in the C equivalent. Then there's things like add a header, remove a header, copy a header. To the earlier question, using these actions, you would tell the system you want a header to be added. And then the actual deparser will notice at the end there was this header added, and it actually needs to go, when deparsing, emit that header when reassembling the packet at the end. There's also the concept of a header array, and you can push and pop into that. So examples of that would be VLAN or MPLS, where you can maybe add another level or remove another level from that stack. Moving along to actions that do not necessarily change the packet fields. You have a count action, execute meter action. That meter could itself then cause a packet to be dropped. There's a few digest-oriented things, truncate a packet. Now there are some actions as well that work on the pipeline and take the packet into different places in the pipeline. So resubmit will actually take the packet in its original state before actions have been applied, and then send it back to the origin. Recirculate happens after the egress modifications have been applied. So you might think they're kind of synonyms in the natural language, but there is a subtle distinction there. In terms of cloning packets, there's also a number of similar variants where you could get clone ingress to ingress, clone egress to ingress, etc. So these ones, as the names indicate, take the packet from the ingress or the egress and then send it back to ingress or egress respectively. So if that's not enough for you, there is also a kind of a get out of jail free card where if you want to make your own action, you can go and do that. Such actions would of course be target dependent and also implementation dependent. So some targets may have hardware blocks that would do actions. For example, an encryption action may be implemented by a block of silicon. Other targets may allow you to use another programming language, for example C, to go and define those actions. So it's important to not abuse this, because that will reduce the portability of programs. But it is there because in some cases one cannot go and express whatever you want to do in the existing primitive actions. Looking now at the compound actions, these actions are basically, in this example, a list of actions, but it could have some logic in there as well, some branching in effect. And such a compound action would be applied based on the result of table matching. So you can see here the actions can affect the metadata fields that the previous section described. For example, the egress spec is a metadata field saying what should happen next to the packet. Setting it to a port number will emit it to a certain port. You can go and modify packet fields, and you can even do the math on those fields, like the TTL is being decremented here. So there are a number of these math type functions. There's add and add to field, subtract from field, etc. So you can tell that it can quickly get quite tedious to go and have to do your expressions as individual function calls, and then you need to sometimes build up your own temporary variables in effect as packet metadata just to hold the temporary results and so on. That's not very nice for a high-level language. So support already exists in some 102 compilers for just using an expression, similar to C or Python-like expressions. And in the 1.1 standard, they all rolled into modify field, where with modify field, you can put an expression as your right-hand operand. Now, before you get too excited here, you cannot go and do everything with this on every target. Some of the targets will tell you, you can't do 9 levels deep nesting of multiplication and XOR and do all that on that specific target. But that applies to other constructs in the language too, that the compiler may tell you this, what you're trying to do is too complex. So some more details about the action execution semantics. In future, with future P4 standards, the actions in a compound action will be executed sequentially. And this is the most natural way to look at it for programmers used to traditional programming languages. It seems to be like a function call or a statement, and statements in sequence. If you're not used to something like Occam, which had the par construct, then you would assume they would be done sequentially. But in fact, up to and including version 102, it's said that for a given table, all the actions would be done in parallel, and then the actions associated with a different table would be done sequentially versus that first set of actions again. So this really confused people that up to 102 action execution was parallel. That's why it was changed back to sequential. So the number of steps that are supported for action execution would be target dependent, similar to the complexity of the expressions going forward being target dependent. Let's now look at how these actions would be used. So a table has associated with it a list of possible actions that can be executed. If you're familiar with something like OpenFlow or Open vSwitch, this will be slightly strange for you, because in those you can give an action list in any table with any actions in any sequence in a flow mod, associate them with a table entry. With P4, you need to pre-declare which actions a table can execute. And then the table rows will specify the key that you want to match on and a single action to be executed when that packet is matched. But that single action can be a compound action. So that's how you get the equivalent of an action list. So the only thing you then end up with that's maybe less flexible than what you had before is you need to pre-declare the permutations and combinations of actions that you want to go and execute. You do get the option to give parameters to that, effectively a subroutine containing individual actions. And using those parameters, you can further influence what is done on a table row by table row basis. So now we're going to have a look at a use case familiar to most of you, the IPv4 use case, where you need to go and match certain subnets, prefixes in other words, and then apply certain actions, maybe drop or do L3 forwarding, L3, L2 together, etc., and then have certain parameters for those actions that are applied. And the control plane will go and populate the table. The data plane will simply go and do the matching and go and execute the actions. So here's an example of how the actions would be defined. You can see they fairly straightforward. It's almost like macros or subroutines in other languages, with the parameters then being used in the individual primitive action arguments. So I'll now turn it over to Gordon. I've been the action hero here, explaining how to be active, and he can be the matchmaker, explaining how to do matching in more detail.
Yeah, I'm not enough of a man of action, so let's talk about matching. So I'll show you a few examples of tables and how you declare tables with different kinds of matches here. So this is the kind of simplest example, an exact match table or a binary CAM, if you want to think of it that way, where we have some collection of fields which are used as a key, and we're going to get actions back. So if you have a look at this, there's a reads construct, and that's telling us what fields are going to be used for the match. And in this case, both of them are going to be an exact match. And then if you've got a good memory or you took a photo of the previous slide, you'll see the range of actions that are allowed in the table here are drawn from the list Johann had on his previous slide for the switch. And what this is saying is these are the actions you're allowed to put in the table. The actual entries in the table are put in at runtime, and you'll be seeing that later on, how you insert new entries into the table, and then the data plane uses the table. So this, if you like, is putting constraints on what actions are allowed. And as Johann said, these could either be primitive actions or compound actions to get combinations. And there's a little example here at the bottom. For this IP case, we've actually got two. We're allowing virtual tables. There's a VRF field there for a virtual table index, and then an IP destination address. And then you see for these random entries that have been put in, the actions that are done. So that's the simplest case where you're doing an exact match. You're only allowed to have one entry of one kind at a time. So I wouldn't be allowed to have the same IP address twice with the same virtual number. You'll see the example here. I realize standing at the back, this is illegible unless you've got the other screen there. But the IP destination address for people at the front is the same. That's because the first field is different. That's a virtual table identifier. So that's a simple case. Then going to the... I see my edits to the slide, which I made yesterday, didn't happen. So if we move to longest prefix match, which will be familiar to people from IP address matching, for example, where you're just interested in the longest prefix. Aha. allow me to look one slide ahead. I think I see what's... Oh. Correction. What I did was I edited the slide content, but not the header. So this was meant to say ternary cam in the header. And you'll see here the two fields are being read ternary, which means we're allowed a wild card on each field to get a TCAM-like effect. So if we look at the examples below, you'll see the second and third columns have a mask associated with the field, and that mask is applied to the field to get a TCAM-like effect. And the first field is obligatory when it's a ternary match, is a priority field. So if there's more than one possible match with the wildcards, the priority field determines which one's going to be selected. So some people might be familiar with TCAMs that give multiple results. In the case of P4, you just get one result according to the priority field. So edit to header, that's TCAM, ternary cam style match. And then the flourish was then there's a special case of ternary match, which is longest prefix match. And you'll see here the second field, the IP destination address, has LPM beside it. And what's going on here is the first field will be an exact match, and the second field is a longest prefix match. And as this build explains, tables don't have to be the same type on all fields. So different fields can have different match types. And you'll see here, if you look at the second column, we've got the normal prefix for longest prefix match on an IP address. And if you like, that's a shorthand for using a TCAM with a specific wildcard match. It's just saying, the first 24 bits or the first 16 bits are relevant. So this is a kind of a common use case, if you like. So here's a list of the first three you've seen with little examples of how you write it down: an exact match, a ternary match, and a longest prefix match. There's another two types of match. One is on a range. So typically, for firewalling or ACL stuff, you have a range of port numbers. So for that, you give a lower bound and upper bound for the match. And there's also valid, as was explained earlier, header fields have a valid bit associated with them. So you can do a test before you sort of march down, comparing all the header fields in the table. You can also check the header is in fact valid and was constructed. So that's the current range. That's the range as of 1.0.2. In 1.1, there's another one called indexed, which is a different story. So you either get a hit or a miss. You've seen how hits get resolved through priorities if there's multiple hits in a TCAM, for example. If there's a miss, then you can put a default action into the table. And this is something that's done from the runtime. As you'll be seeing later, you can insert a default action into the table. So basically, if there's no match found, that default action is taken. If there's no default action, then essentially the table has no effect. So the very useful no-op action is applied. So it means you have a hit, but nothing happens. So that's tables. And as you saw at the beginning, metadata rides along with the packet, and if you like, that's per packet. So each packet has its metadata, and that information only survives with the packet. So tables are one example of a stateful concept. They exist in the background as packets go through. They get updated from the control plane via the runtime API. The other kind of stateful objects which can survive between packets, so you can record state yourself between packets, are counters, meters, and registers. And these are kind of similar in nature, but it's a way of remembering things between packets, so you don't just have this stateless flow of packets through the pipeline. So, roughly speaking, counters, as the name suggests, are incremented with each packet. So they're used for things like counting number of packets, number of bytes total in packets. Meters are for doing traffic management. And in P4, as currently stands, these can classify packets as being red, yellow, or green. So, naughty, fairly nice, and perfectly nice classifications. And then registers are the kind of general mechanism where you can store values and read back values. between packets. So the first two are a bit more specialized, and then registers are the general construct. So to have a look at counters, as a heading may suggest, there are direct counters, and guess what's on the next slide? Indirect counters. So direct counters are counters that are associated with tables. So the idea is, you see there's a table here, it's a random one, it's got 5 ternary fields and a bunch of actions, and it's an ACL application. And what we're saying is for each entry in the table, we want to count how many hits we get on that entry. So how many packets, hit the button, how many bytes in those packets hit the button. So if you look at the counter there, you'll see it's called, this is a bit naughty, packets and bytes, because that's a 1.1 feature. I realize in 1.0.4, you can either have packets or bytes. That's not packets underscore or bytes, that's packets, bytes. So if it's packets, that means it counts packets. If it's bytes, it counts the total bytes in those packets. Packets and bytes was a new feature in 1.1, which counts both. So you have both a packet count and a byte count together. And you'll see the direct construct there is associated with this table called IPACL. So basically what happens is, there's one of these counters associated with each row in the table, and when you get a hit on the table, the counter gets automatically incremented. You don't have to say anything in the P4, it's automatic. And then in expressions, as Johann was just showing you, you can read values of counters and make use of that as you want. So that's a direct counter, which is automatically associated with the table. These builds are pretty deceiving. Everyone will know the phenomenon. You look at the slides on screen, but don't put them in slideshow mode beforehand. So that's just showing you a little example of a table, and there's a counter associated with it. Indirect counters are more standalone counters that you're going to manipulate yourself. So you'll see the new field here is instance count. That's telling us how big the array of counters is. So if you just had a single counter, the size would be 1. If you had like 100 counters, that would be 100. Here it's being set to this constant, which is, I guess BD is, this is a VLAN example, I think, so a broadcast domain or a bridge domain. And here you can see the action that's setting the count. You see the modify field as Johann showed you, and then the count means you apply this counter on the current packet, so it gets incremented if it's a packet counter, or the bytes get incremented. So that way it's decoupled from the table, so you can control it yourself. Decoupled. So meters are similar in nature in counter, though before anyone asks, like, how do you compute the metering algorithm? The answer is it's behind the scenes, a bit like a checksum algorithm, as discussed earlier. So with a meter here, we have a direct meter, which is being associated with the same table we saw on the previous slide. There's an indirect meter example that's saying there's 1,000 meters. And in the direct case, what we get back as a result from the meter is color-coded there, green, yellow, red result, indicating what the meter is saying for the current packet, like what it's got to. It's decided things have gone red because there's too much data going through, or it's gone green, etc. So that's happening in the background. And the indirect one, again, is decoupled from a table. You'll see that action there, execute meter. Again, this is a little naughty. Execute meter was called meter in 1.0.4. It's called execute meter in 1.1. So I know too much. So that's how you read the value there. It's putting the color field into metadata.color, which you can then use yourself later. So similar to how counters are used. And then registers are the more general one. You don't associate registers with tables, they're standalone. So you see here a register declaration that has a width. That static statement, which can be used on the other ones as well, is saying you can only use this construct when you're doing actions on that table. So it gives you locality. It means you can't access the counter or meter from anywhere. It means only when you're doing that table. And you'll see here there's a register read and a register write instruction. That's how you get values from the register or put values into the register. So if you like, registers are the lowest level way of keeping state between packets, and you can do what you like with registers. On that note, matching done, I pass over control flow to Vlad.
Okay. So before I start, we're running a little bit late, but I think we'll finish the control flow function section and then go on break, so that kind of it will be a nice logical break. The other thing I wanted to just say, so Gordon mentioned several times the discrepancies between language versions. So all the examples that are here, they should work on the current behavioral model that is part of your labs. And actually, a number of examples were extracted from that switch.p4 program that a number of previous presenters referred to, so you could kind of see the real P4 code as well. That's one of the reasons we did it for this presentation. So now let's take a look at the control flow functions, because so far we were showing you various constructs, but then the question is, so how do I actually express my algorithm, right? So what am I supposed to do with the packet? Actually, the code that you write in P4 that most closely resembles the code that you would write in any other language like C, that's exactly what control flow functions do. And there are very, very few statements that you can use. So the main statement that is used most of the time is called apply. And apply means that you want to apply a particular match action table to the packet. The table will obviously perform the match and choose an appropriate action and action data that need to be executed. The other thing that is available is the regular if-else statement. And then there is a special form of the apply statement called apply with the case or with the select clause. And I'll talk about that as well. The execution semantics for the control flow functions is sequential. That has been there in the language from the very beginning. But what we'll see in the course of the following slides, compiler has a lot of opportunities to parallelize the code. And it is that ability to parallelize the code is what makes P4 actually a practical language that can be executed on the modern hardware. As of the language specification 1.0.2, there are two standard control functions. One is called ingress, one is called egress. Same way, like you can see, we have a standard function called main, where all the programs start. So in P4, there is ingress. And remember that when Ben was showing you the parser programs, at the end, there was return ingress. That's where you transition to the ingress control function. And so transition to egress function happens implicitly. So let me show you how to define those control functions in a couple of examples. It's actually fairly straightforward. You just use the keyword control. You name the control function. So in your program, I assume that if you're programming for the switch, you'll have these two functions, ingress and egress. And in there, you put the statements sequential like you would do in any other place. So here you can see in a very simple example where we'll first apply a table which performs port VLAN mapping, maybe sets a bridge domain based on the port number and the VLAN ID that you can find in the packet. Then you can apply the source MAC table to perform the learning and the destination MAC lookup. And then in the egress pipeline, perhaps you will do the VLAN tag removal. So that's fairly simple. There's like no real magic in this control functions. The egress function can be called for a single packet that arrives at the switch. egress function can be actually called multiple times. If in the replication engine, for example, you decide to broadcast the packet or flood it to a particular VLAN or to multicast, then for each of the copy that goes on a particular port, the egress function will be called multiple times. So once for each copy. And there is in the standard, if you open, there is special metadata fields that will be changed. It's called the replication ID, and also the indication of which egress port the packet has been committed to. You are also allowed to define your own control functions, unlike how it is done in traditional programming languages. The main reason for that is just to improve code readability. There is really no particular performance advantage or space savings or anything like that. And the functions in the current specification of the language are very simple. There are no parameters. So here what I've done, I've just defined a function called assign VLAN, which performs several types of VLAN assignments, either based on subnet or source MAC address or protocol or ingress port. And then at the end, I probably will define another table which takes a look which one of those 4 tables has been hit and performs the final resolution of what broadcast domain I would like to use. And then in the ingress function, I just check if the packet is not tagged, right? So the VLAN tag header is not valid, and you could see that construct in the if statement. Then I just call my assign VLAN control function, and that's what I've just defined above. So it's a way to improve readability of the code most of all. Besides just straight apply, what we also have in the language is a familiar if statement. And so again, this is actually an example extracted from a real program called switch.p4. And basically what it says that if the type of the packet is IPv4, then we apply v4 related transformations, right? So we apply the routing ACL, we apply NAT, which is obviously only used in IPv4 case. We apply v4 URPF and v4 forwarding tables. And otherwise, if the packet type is IPv6, then we apply IPv6 related tables. So it is obviously a very simple thing, but I want you to kind of think about that because this if statement actually is one of the key optimization tools in the language. So you know how in traditional programming languages like C, for example, whenever you see the if statement, the compiler kind of gets a little bit uneasy because it knows that there will be jumps in the assembly language code, and it tries to do prediction and all kinds of stuff just to reduce the possibility of a jump. In P4, actually, every time there is a if statement, it's a reason for the compiler to do a very smart optimization. And the reason is by having these different functions being called within separate branches of the if statement, it allows the compiler to know that there is no way the objects, the tables, for example, that are used in the function, say, process IPv4 routing ACL, can be mixed together and applied to the same packet as the objects in IPv6. So it shows there are 2 separate branches. And normally that allows the compiler to put the resources related to IPv4 and IPv6 processing into the same hardware stage, and allows it to share the same hardware resources. So that's a very, very key concept of P4, and that is different from traditional programming languages. The other type of branching is called the hit-miss branching. And so what you can do after you executed the apply statement, you can follow it with a so-called select clause. And in there, you can say what should be done if the table was hit, or in this case, miss. So again, even though this looks like a conditional construct, it allows a very good parallelization from the compiler. Effectively, the compiler can decide that the tables IPv4 fib and IPv4 fib LPM can be executed in parallel, and then the results, for example, of the execution of IPv4 fib LPM can be thrown away in case IPv4 fib hit. So in hardware, and again, P4 was designed to be as optimal as possible on the switching hardware. It is usually much cheaper to compute the extra stuff and then throw it away, rather than try to do sequential processing, waiting for the results as we do in our traditional programming languages. So this construct allows us to do that. And a more kind of elaborate construct is, a more generic one, is actually apply with select clause. And so what happens here is we have a table that performs a match on the destination MAC address and broadcast domain of the source port, and there's a list of actions. So basically what happens is when the packet comes into the device based on this destination MAC address and VLAN ID, for example, we can decide if we want to put this packet through the IPv4, IPv6, or MPLS processing. And so what we have in the control function, we apply this table, and if the packet hits an entry which chooses the IPv4 lookup action, then we'll call the function process IPv4. If it chooses the IPv6 lookup action, then we call the tables related to IPv6 processing and so on. So again, what we can do, we can basically perform speculative execution of these control functions ahead of time, and then based on the result in this lookup, we can actually throw away the results that we don't need. That's a very important concept in P4. When you perform misbranching, there are actually two ways of doing that. And so if you look at the code of switch.p4 program, you will see that it uses a style which is slightly different. So one style is kind of explicit misbranching, pretty much what I showed you two slides ago when we use this special keyword miss in our control flow. The other way how switch.p4 program is doing this is slightly different. So the program defines a special action called onMiss, which really does nothing, and includes it in the list of actions that are allowed for a table. And then what it does, it applies the table and says if the chosen action is onMiss, then do whatever you want to do. Why is this style being used? Well, what happens is that per P4 specification, if the table misses any of the functions that are allowed in any of the actions which are allowed in the table, can be used as the default. So this is chosen by the control path, and the compiler doesn't really know which of these actions will be chosen by the control plane to be executed when the table misses. And very often there is only one of those actions. So when the compiler tries to compute the dependencies and parallelize the program, it has to do it very conservatively, assuming that any one of those 4 actions can be the default. In this particular case, the compiler doesn't have this problem. It only knows that it needs to compute the dependencies between this particular action onMiss, which really does nothing, and the rest what might be happening in this table IPv4 fib LPM. So as a result, the compiler can make a much better decision about what can or cannot be parallelized. And so that is the style that the current switch.p4 program employs. And in the further versions of the language, we will allow these default actions to be specified explicitly so that you don't have to use a special coding style. But as of the language version 102, that's the recommended way. Last thing I wanted to show you is that one quirk of P4, very often when you think about writing the program, you think that if a certain condition happens, I want to execute some actions. So for example, if I decided that I'm not dropping the packet, I would like to count, this packet against the counters that are applied to a given broadcast domain or given VRF. Well, P4 actually does not allow you to employ actions directly in the control functions. So this is actually not a valid P4 code. Instead, what you're supposed to do is you're supposed to wrap the actions into a table, and that's how we do it. So basically, we create a compound actions, which does what we want to do. So in this case, increments 2 counters. And then we define a table which does not use any read statement, but only defines this action. So what happens is this table will always be missed if you try to match a packet against it. And so if we set this update counters to be default action on the table, it will be always executed. So what we do, we write our control this way. So if packet is not going to be dropped, apply the table do process counters. And then we need to make sure that the control plane sets update counters as the default action on this table. And so as a result, when you apply the table do process counters, a miss will happen, update counters will be called as the action, and it will perform our update. So that is kind of another thing that is specifics of the current version of the language that you need to be aware of to write the imperative programs. Any questions? Well, I guess by now everyone is a little bit tired maybe, and it might be a very good time for a break. So we'll see you soon.
Good. Okay, I think I'll get going here in the interest of time. So, like one of the topics that has come up across the board here is that the automatic API generation, and I've heard of multiple talkers mention it, and it really is one of the nice things about the API. I'll note the slide deck here has a lot of slides, and they're really good for reference. I'm going to go through most of the first part kind of in detail, and then I might skip over the second part kind of fast. I have a 10-minute clock here in front of me, but they'll be on the line, I'm told, after the show, so you can go on and look at them. So let's get started here. So we've talked about this. One of the really nice things about P4 is that it has a really good structure that maps really well to the API. We can build schemas, and we can create the relationships. So I'll jump ahead. A lot of the concepts we've seen so far: tables, counters, meters, and registers. They're all clearly defined objects. And then we have an unambiguous control flow function. So the idea here in the next couple slides is we'll map these onto automatically generated APIs. These slides use header, kind of C-style header files. There's really no particular reason to use C, other than that's what we're using here, with the sort of thinking that everyone may have a general idea of how C and all works. Okay, so first, tables. What do we want to do with the tables? We want to add, we want to be able to get out of the table, delete, modify, lookup, possibly traverse. So we have a bunch of operations. We have what the table is, the set of match fields it has, the actions, and any data that it goes into the action. So if we were just going to translate this into an API, the first thing we need to do is have all the fields. We need to have the action selector. This will tell you what the action is if that field is matched, along with any action data. So if you're going to start setting fields, you need to make sure that you populate the action data with the values to push into the header, for example. This is how you can get things like push headers. You can do IPv6 rewrites, add labels to IPv6, etc. And then we have an entry ID, and this kind of naturally corresponds to a table. This might be a TCAM, Could be a hash table, could be any numerous types of tables that are defined in P4. So let's take a look. On the left side here, we have a P4 program, and on the right side, we have that translation into a API header file. I'll skip through the build out really quickly. I'll stop there. So here we have 3 actions, A1, A2, A3, each taking some amount of input. So A1, for example, takes P11 and P12, so 2 fields. A2 takes 3, and A3 is sort of a void action. The table then is defined. It gives you the fields that it matches on. So let's see, how do we translate this? So one way to do this, and there's more than one, is let's roll this out, is to define each of the actions as an action spec along with their fields, like this. And then you can see here that, let's see, I think I have a pointer. I can give it to you. Okay, here we go. So here we have action 1. It takes P11 and P12. It's a type def. I have a type def for A2, a type def for A3, and then finally we have the T1, which corresponds to this. And you can see we have meta, 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 H1 valid. Okay. Make sure I get the right buttons here. So we can continue to do this for the same thing now that if we add actions to the table, which we want to do. Oops. And you can see we added them here. A1, A2, and A3. So we'll see this sort of happen in a couple of the demos, I believe, as well, where people are auto-generating this type of header file from the P4. Now, for each sort of operation, you're going to want to generate a new set, oops, sorry, too far, fields. So here we have all of our modify functions. So entry modify with A1, entry modify with A2, entry modify with A3. And each one of these corresponds to the actions. As you can see, this continues to blow up as we do it now for delete and lookup. Oops, sorry. So we need these actions as well. Delete. I notice you give it the target, the session, and the entry. This is the handle into the table to delete. And this gives you the lookup, which returns back the spec for that particular handle. So you can kind of see the flow here. So we've gone through, if I roll back a little bit, modify, oops, this might be too painful. If we go through modify, we did add, we did modify, and we've got delete and lookup here. So now we have a set of functions to do all of those operations. And this is basically what you would want to do with a table. So you add an entry, you delete an entry, you look up and see what's in there. And the last operation, that I think is on this, is the get, which is going to return, oops, right here. So, and we can continue to run through this, and I'll say for each operation, you can see what we're doing here is we're building up a set of functions for that operation, for the specific table and these specific actions. Keep going. I'll do it for each one. Okay. So that was tables. And you can imagine that the same compiler, if you remember back to I think the very first slide that was shown, or the first set of slides, that your same compiler that's generating your target code will likely be generating this API as well. And because we have more than tables as objects, we do counters with another set of operations, get, clear, and set. These seem to be sort of the canonical operations you want to do on a counter, along with their array operations. Now, I'll jump through these fairly quickly because it's the same sort of translation style here. On the left, you have the program, and on the right-hand side, you have the header files. Oops. And like I said, these will be posted online, so you can go through and actually look one by one to see what the actual translation that we made is. But the kind of key takeaway is that the compiler can generate the right-hand side from the left-hand side and give you sort of the functional operations on that object that you would like to use. Again, we can do meters as well, and registers. And so let's just pause for a second as we flip to the last couple fairly quickly. What are the pros and cons here? So the first thing is that they're easy to understand. So you end up with a function that maps to the operation you want to perform and on the object that you would like it to operate on. The other benefit is you do get some type checking. But the biggest con, as you probably even recognize as we flip through, is that you end up with lots of functions per table, which may or may not be a con depending on where this is, what you're doing with this API. The key point here is that it's sort of inconvenient to build CLIs on top of this. So there's another style of APIs that we can generate as well, which are slightly different. So here we have a set of actions, same set of actions, same table, and we'll take a look at the implementation. And this is more closely resembles how I did this in one of our demos, is that the action here, action A1, A2, A3, then you define all of the actions as enums, give it a type def for the table, all your tables get type defs, and so you end up with this long string of enums for every different type. Okay, there's more. Then you end up with action to string type things to turn all of these into readable form. A whole set of another type defs, and then more generic than the previous ones, you end up with entry action set, entry field set, entry add. So this is giving you the operations again, but in a slightly different form using the enums on the previous page. And we get another set of operations: add, modify, delete, get, lookup. And you can see here, instead of having the multiple sets of each one, we have sort of one that is then using the enum. So we could do that for the other things, to do get lists of tables, get lists of actions for tables, and so on. So those are two styles of the sort of APIs that we are sort of known to be in use. So what is the pro of the second one there? It's extremely flexible. It doesn't depend on a program. It can so you can sort of incrementally add things by adding fields to the enums. And it makes very easy CLIs, and I'll show you one of those later today. Another advantage, because it's easy to add, you can actually sort of debug and work with these things on the fly and recompile your tools, or not if they're in something like JSON or XML that you don't necessarily need a header file for. It does have some cons here. There's no type checking, or very little, and requires a bunch of function calls. And I'll just conclude that I think the big takeaway here is that from the P4 objects that we can generate the API, we sort of have these two styles, and there might be some hybrids in the middle that try to strike a balance. You may be able to get more type checking out of the latter one, or make the first one more fluid. It really sort of depends on what your target is. If you're looking to make a CLI, then you might want to have your API informed by that. If you're looking to implement something for netconf or thrift or something like that, you might generate a slightly different API. And I believe we'll see a few of those this afternoon. So that's the APIs section. Any quick comments or anything? No? Okay.
Okay, and so I'll conclude just to talking to you a little bit about how the compiler works, and I think it's important because, as you just saw, besides compiling the program into the hardware, the compiler also provides you with certain information that allows you to generate the APIs. And one of the things that I think we're looking forward is actually customers being able to generate the APIs in the styles that they like. So these two examples that we just saw from John is just two examples. So to facilitate the language development, the P4 consortium actually designed a modular compiler which consists of a single front end and multiple backends. So the front end, currently it's named P4 HLIR, and the reason is because its job is to transform a P4 program into high-level intermediate representation. What this hardware high-level intermediate representation is really a set of Python objects, and it's somewhat similar to abstract syntax trees, but there are some additional attributes which are more kind of P4 specific. And this is a fully documented hierarchy of the objects, so that if you get the P4 HLIR source code, in there, there's a PDF file fully describing HLIR. And so this is the component that we expect anyone who plans to either develop their own P4 compiler or to enhance or create the existing compiler, or maybe create some other Python tools to be able to use, and so that people don't have to bother themselves about, how to parse P4, how to do the basic checking, like for example, this table has been referenced but not defined, and so on. And then what the other part of the compiler is just backends. And so what backends do, they go and take HLIR as the input, and they're able to generate a specific code or specific configuration for a variety of targets. So one of those targets, actually even two I think now, are available in the source code form freely. So on p4.org site, there is a software switch that you will be using, software switch model that you will be using today during the labs. It's called BMV2 because it's a second version of the behavioral model. And so for it, there is a compiler which transforms P4 program into a JSON file that the model understands. There is also an experimental compiler which translates P4 into eBPF, and that eBPF can be loaded in the Linux kernel. And then, of course, various companies are working on a variety of P4 compilers for various targets. So, for example, I know that Gordon, who spoke before you today, he is working on the P4 compiler for Xilinx FPGAs. So there are many others. Then the other thing that can be also built using HLIR are some other perennial tools. For example, there's a graph generator. So I briefly spoke about dependencies, and so that's what graph generators can produce. And then there is, I'm not sure what cut out of the slide, but basically they're runtime API generators. Currently, they're fairly tightly coupled with the rest of the compiler code that produces the code for a particular target, but that doesn't have to be so. So we hope that they will be kind of separated in the future. And so that's how things look like pretty much. So P4 program gets transformed by P4 HLIR front end into this high-level intermediate representation, and all of that we have those we have those backends which compile the code for a variety of targets. Yes.
So does the FPGA version, does it like intermediately generate like an HDL or Parallel or something?
I think you have to ask Gordon.
Or I guess the other question is that it seems HDLs of some sort seems to be a missing target
There are companies that work on the ASICs, and so they do have their own languages and special representations to represent the ASIC configuration, absolutely. The output of the compiler for a particular hardware target is very, very target dependent. That I can assure you about that for sure. Here I just wanted to kind of briefly touch upon this dependency analysis thing that might be helpful for you to write more efficient P4 programs, but also shows you how actually it's possible to fit P4 into the particular target hardware. So dependencies, that's what the compiler can infer from a P4 program and use this analysis to parallelize the processing, which is really the key in compiling P4 efficiently onto any modern hardware. So there are 5 types of dependencies that the current compiler can identify, and we'll just go through them one by one to show you what it means. So the first is really not a dependency because the tables are called independent. So what you could see here are 2 tables. So one I call destination MAC, which basically matches the packet Ethernet destination address, and either does nothing or it can set the egress port to a certain value. So basically direct the packet to go out of a certain port, right? And then the other table is called MAC filter, and it's a source MAC filter. So it uses the source MAC address, performs the exact match, and then either does nothing or drops the packet. And it drops the packet by just setting some metadata field to 1. And our control program it has to be sequential, right? So we say apply destination MAC table and apply source MAC filter. But if you look at these tables, they actually match. They use totally different fields to match on, and they use totally different fields to actually express the result. So that means that if you execute the first table, DMAC first, or SMAC table first, and the other table second, it doesn't matter. So they can be executed in parallel. And so the compiler detects that specific fact, and if you use the program called P4 graphs, it will draw 2 blobs, 2 bubbles, and connect them with this dotted line, meaning that these tables are independent. And so if the obviously if you do use a software model, it's probably not going to help much. But if you use a hardware which can do parallel processing, it will actually know that these tables can go into one stage of the pipeline and be processed in parallel. Now we can modify our program slightly. And what I did, I just added the ingress drop action to the table DMAC. So before it didn't have this action, now it does. So what happens is it might be that both tables, if they match a packet and both decide to execute the ingress drop action, they will be modifying the same metadata field. And obviously when the same metadata field is modified from 2 different sources, there could be collisions. So that's what is called the action dependency. The action, in fact, there is a conflict between those 2 actions. And so the compiler detects that and graphs it now slightly differently. It draws this blue arrow and shows which field creates this action dependency. And so as a result, the compiler will be forced to not parallelize those tables and put them in separate stages in hardware to make sure everything is done cleanly. The third, actually most common dependency will happen in a slightly different program. So I decided to expand my program further, and I added another table called port bridge domain or port broadcast domain, BD. So before I start doing the lookups on the destination MAC, I would like to perform this lookup now using both destination MAC address and broadcast domain. And I assign broadcast domain beforehand by just mapping a port to a broadcast domain. So effectively, in more plain switching language, I use port-based VLAN assignment. That's in the first table, and then I perform destination MAC lookup, and the last table, source MAC filter, stays the same. So what happens now is the compiler sees that this metadata field, ingress metadata BD, that is needed by the table DMAC has to be computed previously, beforehand, by the table port BD as the program indicates. So we apply port BD table first, DMAC second, and SMAC filter third. And so that means that the DMAC table is absolutely dependent on port BD, and it's called match dependency. So for the table DMAC to perform a match, it has to wait for the results from the port BD table first. And this is indicated by this red arrow, again with a conflicting field name afterwards. And the third table, SMAC filter, that I didn't really change from the previous example, it is independent. So what the compiler, kind of the mental picture of the compiler is that if you have a hardware with two-stage lookups, the port BD must be in the first stage, DMAC must be in the second stage, and SMAC filter can be placed in either place. The other dependency I kind of briefly talked about when we discussed the role of the if statement. So it is called successor dependency. So what happens here is we have the same tables as on the second example. So the DMAC table and SMAC table, and they both use this ingress drop action, so they are conflicting, frankly speaking. They have this action conflict. But the code and the control function has been changed. So in the control function, I say, well, if the broadcast domain is not equal to 0, then I want to apply the DMAC table. And if the broadcast domain is equal to 0, then I would like to apply only SMAC filter. So by putting those potentially conflicting tables onto separate branches of the if statement, I made them non-conflicting. Now they can be placed into the same hardware resource. And that's exactly what this picture shows. And the way it's graphed by the current tools is there's this green two green lines, one with a circle, one with this diamond, which show you two paths that become independent because there is an if statement preceding them. And the last is called the so-called reverse read dependency. I changed the program once again. So instead of having the table called SMAC filter, I decided to use a table called SMAC mangle. And so what this table does, it uses the action set BD, the same action as the port BD table. And basically, it can modify the broadcast domain field in the metadata. So what happens now is that because this table doesn't have the ingress drop action anymore, it's not conflicting with the table DMAC. But we have to be very careful because the table DMAC matches on the broadcast domain field, and the SMAC mangle has a potential to change that field. So because in our control program, we say that we want to execute DMAC and then SMAC mangle, and the semantics has to be sequential, that means that we must put SMAC mangle into the third stage after DMAC. Otherwise, it has a potential to modify the field before it has a chance to be used for the lookup. And so there is this yellow arrow which connects the tables DMAC and SMAC mangle. So this is kind of the last dependency that the compiler can identify. And so subsequently, depending on how the hardware actually performs, it can do a variety of things, but the goal is to parallelize your program, and it can do it quite efficiently. So that concludes our presentation about the language. We covered the basic language constructs and the API generation and the tools. And if you have any final questions, please feel free. Yes?
In previous slides,
Yes.
because your SMAC lookup potentially affecting a new BD, so with that, you should use the SMAC mangle lookup first, then DMAC.
Well, in this particular case, so the program says the control plane, right? The control function, I'm sorry. It says apply port BD, apply DMAC, and apply SMangle, right? And so we have to make sure that the compiled program has the effect as if these tables are executed in this particular sequence. If you think that your algorithm will work with a different sequence, right? So in your algorithm, you would like to do SMangle first, then by all means, but you have to express it yourself what you would like, right? So same way like when we program in C, we have to watch the order of the operators. Same way in P4, when you put them in a certain order, that means that that's your intention. Yes?
So thinking about, actually trying to, build hardware that uses P4, the two things I'd really care about are sort of managing ingress and egress queuing, and also managing scheduling my switch interconnect. So if I have like multiple egress queues, and what's the priority of packets, and things like that. So that's one sort of missing thing. I couldn't even really figure out how to output it, how to submit a packet into an output.
Okay.
Or which one's the input queue I'm actually.
So the question is how to express the queuing mechanism in P4, I guess. So the answer is P4 really does not have any ways right now and the constructs to express the queuing mechanism inner workings. But what P4 allows you to do is it allows you to define the signals that will go between the ingress pipeline into your queuing engine and the signals that will go from your queuing engine into the egress pipeline, and that's what is called metadata effectively. So, and then you can just define what those signals will mean in your particular case. P4 standard defines a certain kind of standardized model, which includes, among other things, the set of signals that should be used to communicate with the queuing engine, but you should be free to extend that to as your needs dictate.
You mentioned at the beginning of this presentation that one of the P4 backends emitted eBPF, but P4 seems so much more expressive than eBPF. How is that possible?
That's a good question. So the question is how P4 is mapped onto eBPF. I hope I'm not going to take anyone else's presentation because I thought we wanted to discuss the mappings. But the quick answer is that only as there is an intersection between eBPF and P4, and that intersection is what is being translated. So yes, it will be somewhat a subset of P4, and it uses a subset of eBPF. Okay, the last question, I guess, because Chang is showing me that time is up. Yes, please.
So I have a question on APIs, actually. And the APIs seem to really define downward signaling from like the control plane to the data plane, sort of. But how about upward signaling? Like if I'm, I want triggers or
okay.
or statistic streaming.
So the question is how P4 program can communicate upwards and define notifications with the control plane. The answer is there are a number of mechanisms. So one of the most important mechanisms is operation, the primitive action called generate digest. We didn't cover it in this presentation explicitly for the lack of time, but once you get the PDF, it will be there. Yeah, absolutely. Yeah, besides sending the packets to the CPU, of course. Yes. The question is how swap operation is supported. Very good question, because once we change the semantics of the compound actions from parallel to sequential execution, it became a little bit problematic. The answer is if you want to do a swap, you do it exactly like you do it in C language. So typically you would declare a temporary metadata field where you will copy the old value, right, and then copy the new value into the old value and back. And the compiler should have the smarts to understand that this temporary metadata field is only used in one place for a very short period of time and generate the most efficient code, hopefully, for the target. Thank you very much.